Welcome back, everyone, to this continued discussion of Gini impurity. Specifically, we're going to begin to look at how Gini impurity is used in decision trees. So in order to begin to understand the ordering of nodes and how splits are conducted within a tree, we're going to explore how a decision tree is constructed slowly from a training dataset using Gini impurity. And there's lots of things we need to consider when first constructing a tree, such as deciding what feature will first be used as the root node. And we can actually use Gini impurity to compare the information contained within the features for the training data. We would obviously want to use some sort of feature that contained a lot of information in order to actually perform the split. So let's explore this concept a little further. As we already know, the formula for Gini impurity for classification is the following equation. So for a set of classes capital C for a given data set Q, we can say the Gini impurity of that data set Q is equal to the sum of the probability of belonging to a class lowercase c times 1 minus the probability of belonging to that class C summed up for all the potential classes. And we already know that we can essentially calculate this manually and then plug in those probability values. As we saw in the previous very simple example, we had, for instance, those 4 data points, and we calculated the probabilities of belonging to class red or class blue. Now what we're going to do is take a look at this data set, which is a little more representative of what we would encounter in real life, and see how we could construct the Gini impurity of a particular feature. So we're going to create a decision tree to predict whether or not an email is spam. And there's really only one X feature to use for a node. And for the purposes of convenience, this particular feature only has 2 potential values, either yes or no. So that means if we were to split on this feature, there's only 2 possibilities. One that splits to yes and one that splits to no. So essentially, this root node is going to ask, did the email contain a URL link? So in order to predict if an email is spam if it contains a URL, we have to ask this question at the node. Does it contain a URL, true or false? Let's first take a look at the instances of true. It did contain a URL link, or the URL link value for X is yes. So if I take a look at my feature values for emails that contain a URL link, I can see that 2 of them were spam emails and 1 of them was not a spam email. So maybe it was a boss sending you a link to a YouTube video or to a conference link and you could check it out. Then we're going to ask the question, what about the emails that did not contain a URL link? And for the most part, they're not spam. So 3 of those emails are no, and 1 of them is a spam email. So there was a spam email that for some reason didn't actually contain any URL link. Now the next step is to actually calculate the Gini impurity for the entire feature of URL. And what we're going to do is calculate the Gini impurity of each of these nodes after the split, and then we can take the weighted average of those Gini impurity values to get the overall impurity of the URL feature. Obviously, if a data feature is more impure than other features, it's probably a good feature than split on, because you're getting a lot of information off of this split, creating a lot more purity post-split. So recall the Gini impurity formula, where you essentially take the sum of the probability of belonging to each of the classes times 1 minus that probability. What we have here are really 2 classes in that set of capital C classes. We have the yes spam class and the no spam class. So let's begin our calculations for the left leaf node. We start off by calculating the odds of belonging to the spam class. So that's 2 out of 3 of those emails were spam. So we say 2 out of 3 is the probability of belonging to the spam class. So then we'll say 2 over 3 times 1 minus 2 over 3. And then we need to add it to the other probability class, which is the no spam class. And that's going to be 1 over 3. So just as we did before, all we're doing here is we're doing the Gini impurity formula summation for all the potential probabilities of the classes. In this case, there's only 2, yes spam class and no spam class. Then you'll notice here that on the left leaf, we have a Gini impurity of 0.44. Then we're going to repeat this for the right leaf node. And in this case, for the right leaf node, we have 4 total emails, which means the probability of belonging to the yes spam class is 1 over 4, and the probability of belonging to the no spam class is 3 over 4. And if you calculate that out, you should get a right leaf Gini impurity of 0.375. Now that we have the impurity factors post-split, we should be able to actually calculate the Gini impurity for the overall feature. So what we do is we calculate the Gini impurity by taking the weighted average of both of these leaf nodes, that is 0.44 and 0.375. The total number of emails in the entire dataset was 7. Note that after the split, I have 2 plus 1 in the left node, or 3 emails, and then 1 plus 3 in the right node, or 4 emails. So 3 plus 4 is 7, which means I'm going to take the weighted average of each of these Gini impurities based off how many emails are represented in each of those nodes. So if I take a look at this, notice I have 3 emails in the left node, 4 emails in the right node. So a weighted average formulation would say 3 over 7 times the left lead node's Gini, which is 0.44, plus 4 over 7 times the right leaf node's Gini, which is 0.375. And if you calculate all of this, you'll get a Gini impurity of 0.403. So the Gini impurity for the overall URL feature is 0.403. But what if we had multiple features? So we still have actually a lot more issues to consider. Here we showed you a very simple example where the feature itself was a very convenient case where it was only 2 potential values, yes or no, on that feature. But I haven't really discussed yet how we actually deal with multiple features in order to decide which feature should be the root node. I also haven't explained how we actually calculate Gini impurity for continuous features or multi-categorical features, where maybe instead of yes or no, I have blue, green, and red. So what I'm going to do is incorporate the Gini impurity to each of these issues to solve for the best root nodes and the best split parameters for leaves. So we've just seen the very basic case on how to calculate Gini impurity for a feature where that feature only has 2 potential categorical values, true or false, yes or no, 0 or 1. Now what we need to do is show this calculation for other potential feature types, where we have, that is, multiple features. So how would we actually compare multiple features' Gini impurity values against each other to choose the root node, and then for the actual specific feature types themselves, where I could have a continuous feature or a multi-categorical feature, which is not just a binary class feature. So let's go ahead and move on to part 2, where we're going to discuss how we actually do this calculation. So I'm going to see you in the next lecture where we continue this discussion.